Learning mixture of Gaussians with streaming data. We are interested in clustering data points into K clusters. We make the standard assumption that the data comes from a mixture of spherical Gaussians with some unknown variance sigma. Centers of each pair of these clusters are separated by more than c sigma for some constant c. In this work, we are interested in the streaming setting where all the data cannot fit into the RAM and we need to be space efficient as we process data points from a stream to estimate the cluster centers. We provide the first bias variance bound for clustering in the streaming setting by analyzing the convergence of the streaming version of the celebrated k-means algorithm. The streaming version proceeds as follows. Given some estimates of the centers at time step t, when we see a new data point from the stream, we first find the cluster it plus 1 whose current center estimate is closest to the new data point. In this example, it plus 1 is 1. We then imagine assigning this new point to cluster it plus 1 and update this cluster's center estimate by moving it in the direction of the new data point by an amount dictated by the learning rate. We bound the expected error in the center estimates as we get more data points from the stream when we use the streaming k-means heuristic. For a small center separation of square root log k, and for polynomial in k and d samples, a suitable initialization gives us the following bound on the expected error. In particular, this bound decomposes into a bias term, which is dependent on the initial error and decays at a rate polynomial in n, a variance term due to noise in the data points, which goes down at a nearly optimal rate with extra log factors, and finally, an offline approximation error term, that is the error present in any algorithm that performs a hard assignment of points to clusters. Our analysis of the estimation error is based on the following. This problem of clustering is non-convex, and therefore we can only show decrease in error when the estimates are within balls of some small radius around the true center. Even if we initialize the estimates to be within this ball, large noise in a single step can push the estimates outside the ball. In order to handle this, we first initialize within a smaller ball to allow some slack. We then use a careful martingale argument to show that, with high probability, at any time step t, the estimates do not move away by more than the slack and hence the bound.